Hello, everyone, and welcome to another wonderful day of PChem. So today, what we're going to be doing is taking our knowledge of a one-dimensional particle in a box and expanding it out into multiple dimensions. So one of the simplest ways we can do is go from a one-dimensional system to a two-dimensional system. So our two-dimensional particle in a box is going to be actually quite analogous to our one-dimensional system, where I have a particle that acts as a free particle with a potential of 0 within a distance of 0 to L. But now instead of it just being in in the X dimension, where I go from 0 to L, I now have it with respect to two dimensions, X and Y. So because my box may not always be a square, it could be a rectangle, I'm going to denote the X dimension as LX and the Y dimensions as LY. And so inside this box, I act as a nice little free particle. Outside the box, I have an infinite potential, so there's going to be 0 probability of finding the system outside the box. So all of my particles should be located somewhere in this infinite potential well. So from here, we can use a lot of the same tricks we use to examine a one-dimensional particle. First of which is that inside this well, since I've got no potential energy, I have a fairly good general Hamiltonian. So we start with our good old negative h bar squared over 2m. But now instead of just having the system with respect to a second derivative with respect to x, I also have to introduce an additional term, which I'm going to add in of a second derivative with respect to y. So I'm examining not just the motion in the x direction, but also on the y. But one of the biggest things is that these two components are additive. Now, because they're additive, that also means that I can separate them out. So I can have a Hamiltonian that's just an x Hamiltonian in the x direction. And this is going to be the same Hamiltonian I used for the one-dimensional particle in a box. And then I'm going to add in an almost identical Hamiltonian with respect to the y direction. Only big difference is I've now flipped the second derivative with respect to x to the second derivative with respect to y. So mathematically, it's going to function identically, except for it's going to only examine behavior in x and y instead of x. Now, one of the biggest benefits of being able to separate out this Hamiltonian is that what it means is that instead of dealing with one big complex equation, I've split my system into solving two simpler problems. Because if I can solve my one-dimensional Hamiltonian, I can do that twice. I can solve my general Hamiltonian. So that's actually not too bad. However, now that I have a Hamiltonian, we have to always ask our same question: what's my eigenfunction? So we actually get kind of lucky in this case, because since I can separate out my Hamiltonian as a sum, it means I can separate out my wave function in terms of an x component and a y component. So this means I'm going to have no terms with the shared xy component, so no sine x xy. Everything can be separated out into two general terms. This is always nice, but won't always be the case as we go forward. But gotta love it when it can happen, because what we can then do is say, well, I have a wave function with respect to the x direction. Well, this means it's probably going to be an eigenfunction of my Hamiltonian with respect to the x direction. Well, I know this Hamiltonian, it's my one-dimensional Hamiltonian. So let's go ahead and put in a one-dimensional wave function. So I'm going to do this with respect to the x for the x wave function and with respect to the y wave function. The biggest thing to note is what changes. So with respect to the x direction, we're now dealing with the length of the box in the x direction and the energy state in the x direction. It's worth noting that that does not have to be the same as the length of the box with respect to the y direction and then energy state with respect to the y direction. So we're going to see as we go forward, there's plenty of cases where I may have a high energy level with respect to x and a low one with respect to y, which is going to yield some fairly interesting results. However, in the meantime, this does actually give us a way to express a combined wave function for a two-dimensional Hamiltonian. It simply can be produced by multiplying our two wave functions together. So we have a combined normalization constant and just the product of the two sign terms. One is only with respect to x and one is only with respect to y. And it turns out this is going to come in big handy when I'm trying to apply my Hamiltonian to our new wave function. So we're going to be focusing on kind of the shorthand notation, where again, just as a reminder, the x Hamiltonian is only going to act on the x wave function. Because if I try and take the second derivative with respect to x of a term that only has y variables, well, I'm going to get a pretty nice and simple answer. So because of this, what I can then do is start with my basic Schrodinger equation, then input my general expressions for the Hamiltonian, the wave function, and then I'm going to distribute my wave function over the Hamiltonians. So now I've got the x Hamiltonian acting on the combined wave function, the same thing with y. Now when I do this, for this first term, it turns out that the y expression is just a constant since there's no x's in it, so it gets to be pulled out front. And the same thing with the x wave function when we're dealing with the y Hamiltonian. Now here we actually get fairly lucky because my x wave function is an eigenfunction of my x Hamiltonian. So I'm going to produce my corresponding eigenvalue. And the same thing with y. Now here, my eigenvalues are just constants, so they aren't going to play a major role. And I still have the x wave function times the y wave function. Well, that's in both the first and the second term, so I can pull them out on their own. And as a reminder, this is just my general wave function times now the sum of my x and y energies. Well, hopefully this looks a little familiar because I've got an operator times psi produces a numerical value times psi. Well, that's a Hamiltonian solution. So it turns out that the eigenvalue for a two-dimensional Hamiltonian is simply the sum of the one-dimensional energies. So this means if you have any kind of multi-dimensional system where you can separate out the Hamiltonian and wave function into their component parts, the resulting eigenvalue is just going to be the sum of the one-dimensional eigenvalues. And so you're going to note that as we go forward, separability of wave functions and Hamiltonians is going to be a very big feature. So this means that I can generate, again, my total energy in terms of my one-dimensional eigenvalues that we addressed last time. So we're going to go ahead and throw those in here, again, noting that each eigenvalue may have a different value in terms of the energy state and the length of the box. However, everything else is constant, so it can go ahead and be pulled out as a common shared term. And all we're left with is then trying to sum up this ratio of energy states to length of boxes. However, we can often simplify this a little bit more if we run into a very lucky scenario called a square box. So a square box is exactly what you think. It's going to be a box where the length in the x and y direction are common. This is often referred to as a square well potential. So again, this is going to be where the potential well is the same dimensions in x and y directions. We love this scenario because that means that since these two terms are shared, they also get to be pulled out front as a constant. So what we're left with is the energy being expressed in terms of a constant value times the rate times the addition of the ratio of the times the sum of the squares of the energy levels. So this is actually kind of a nice general description in terms of energy and wave functions of a two-dimensional box. However, I've pretty much just thrown a whole bunch of equations at you. So let's take a step back and see what everything looks like. Let's start by looking at our general wave function. So our general two-dimensional wave function has a normalization constant and a x dependency and a y dependency. Now, since these are sign terms, what we can do is look at what the location of nodes and maximums as we essentially change the energy states. So in the ground state, nx equals 1 and ny equals 1. And in this case, we should expect a maximum at the center of the box, no nodes present. And so that's going to happen in both the x direction and the y direction. So the maximum is going to happen right smack dab in the center of the box. However, let's go ahead and excite the system up to nx equals 2. And at this point, what we end up having is is a node at the center of the box with a positive wave function on the left-hand side and a negative wave function on the right-hand side. And in the y direction, ny still equals 1, so it's the same as in the ground state. So this is going to have a slightly higher energy as I'm now moving more of the wave function in the x direction towards the edges of the box. And well, in the y direction, the dominant wave function and thus probability density is at the center. This then gets inverted when n of x goes to 1 and n of y goes to 2, where now this in the x direction, we still have a density centralized along the middle of the box, whereas in the y direction, the density then moves more towards the 1/4 and 3/4 point of the box. Then if we have nx and ny equals 2, we have a node cutting through the halfway point in each direction, and positive wave functions in the two corners, negative in the other two corners. Noting that we do have a positive in this upper right corner because both of the two wave functions give you a negative, cancel out, give a combined positive. So we end up having a lot of kind of symmetric behavior, which is actually fairly useful. And again, the probability density can then just be taken as the square of these wave functions, which again is going to kind of increase the gradient on the wave function, moving more of the density towards these peak locations. And this has some fairly interesting consequences as we start to increase the number of nodes, as we're going to slowly shift the where the density of the particle is located, as well as the variance of the system. Similarly, this gives us back our energy, where we essentially combine the energy with respect to the ratio of the energy level and the length of the box. Now, this has some very interesting consequences in terms of a square box, because in terms of a square potential, all of this term is now shared, and we end up this ends up yielding some degeneracy issues, as it turns out we have the same exact values possible for n of x as n of y. So we're going to have a lot of degenerate energy levels, which, as a reminder, is going to be identical or different states with identical energies. So one of the big things is you can imagine a system with an energy of 10 h bar over 8 ml, which actually should be 5 halves energy. And this is going to have two solutions. The first of one being, 3 and 1, and the other one being 1 and 3. So we have two different solutions, different number of nodes, but with the same energy. And so this is one of those important things to note, is even if you know the energy of the system, you may not know the exact wave function that yields it. Not to mention, as we saw last semester in statistical mechanics, the more degenerate a state is, the more likely it is to occur, as there's more of these states to be populated as the temperature increases. However, this is all just for a two-dimensional box, but we live in a three-dimensional world. It's actually possible to extend the ideas of a two-dimensional box to a three-dimensional system simply by adding in a z term. So now I have my total Hamiltonian as the x Hamiltonian, the y Hamiltonian, and the z Hamiltonian. Simultaneously, this is going to provide me a wave function that is an the x solution, the y solution, and the z solution to the one-dimensional to the one-dimensional Hamiltonian. Or one-dimensional particle in a box. And you can imagine you can continually kind of scale this idea up if you had more dimensions. However, we did just kind of run out of spatial dimensions, so this will have to do. Very similarly, we're going to have, we can then express our probability density as simply the square of this wave function. Where now we guarantee a positive solution to the probability density by essentially squaring the sign of each of these terms. One of the things that you should make note of is that just like it's possible to have a square potential by setting 2 lengths equal, you can have a cubic potential by setting these 3 lengths equal. And this would be essentially the probability density of finding a particle in a uniform cube with an infinite potential outside. And this also gives us similar ways to solve the energy of the system, simply by summing up the energy eigenvalues for the X, Y, and Z solution to one-dimensional particle in a box. And this is going to be a feature that we'll make great use of when we move into atomic and molecular systems, is we're going to be desperately looking for systems where we can separate out the Hamiltonian, because if I can make my Hamiltonian additive, it means I can tend to make my wave function multiplicative, which generates an additive energy. And this is just such an easier set of problems to solve. However, next time we're going to be dealing with the fact that it turns out that not all potential wells have infinite walls. Next time we have to deal with the idea that our walls may actually have a potential function that we have to acknowledge. Until then, take care.